Hello, welcome to the another session of thermodynamics. Today we will be dealing with the second unit's problems, which is on work and heat. So we have taken a very simple problem by using the concepts whatever we have learnt in the second chapter, that is work and heat. By applying into the problem, we will be finding the solution to this problem. So let us always the solution begins, or the process of finding the solution begins with the clear understanding of the problem. So it is very important to understand the problem by reading it once or twice and understanding it in a right way to find a right solution. Okay. Consider gas examined in a cylinder as a system. Always in thermodynamics, whenever I am speaking about work and heat, the very simple example which we take is piston cylinder arrangement. Let me take a piston cylinder arrangement. Now this is the piston cylinder. So the basic tendency is to confuse or understand this piston cylinder itself as a system, but it is totally no factor. Why? Because always in thermodynamics we call the gases or the working fluid or consider it to be as a system. Suppose if I ask what is the system of our body, then we need to think it as blood, not the body itself. A system being a system of a piston cylinder arrangement will be always a gas or any fluid. Okay, here this is the device and the working fluid. The working fluid means the fluid which is responsible for the conversion of one form of energy to another form of energy will be called as a working fluid. As I said, for a human body, blood is the working fluid. For a steam engine, steam will be the working fluid. For an internal combustion engine, the combustible gases will be the working fluid. In the similar way, for a refrigerant, for a refrigerator, refrigerant will be the working fluid. So the fluid which is responsible for the device to work will be called as a working fluid, and here that working fluid itself is the system for this particular problem. That is why this sentence has been quoted, that is considered gas examined in a cylinder as a system. Okay. The initial pressure is being 210 kilopascal. So let us write down the data. So initial pressure, I will represent it by P1, which is 210 kilopascal. So 1 I have represented to state that it is in initial condition. The initial pressure is being 210 kilopascal and corresponding volume is 0.04 meter cube. That is corresponding volume to initial pressure, even that too will be initial volume, that is V1 is equal to 0.04 meter cube. Full stop. Calculate the work done when the volume of gas increases to 0.015 meter cube. So after increment it will be defined as state 2. So the final volume V2, it will be it is given as 0.015 meter cube. Full stop. Calculate the work done when the volume of gas increases to 0.05 meter cube. Okay, this sentence has got repeated. Let it. Okay. So, the very first point to be found is by heating at constant pressure, and next, so I am supposed to find the work in these two different conditions. What are those two different conditions? When the expansion or when the volume changes from 0.04 to 0.015 in two different ways, that is when by heating at constant pressure, the second one is when pressure varies inversely with volume. So, the amount of work outcome in these two cases, it will be different. So, let us picturize the problem. So, I will write the initial volume as V1 and the final volume I will denote it as V2, and this dotted representation of piston is representing the position of the piston in the final position or when the process is completed. This is the initial position, this is the final position. So, this is the amount of increment in volume of the working fluid. So, we can just say this as V2 minus V1. This is the change in volume from initial to final. We also know that the work definition is integral of PdV. That means here we have not written the limits. The reason is work done and heat transfer both are path functions. In this problem, we are clearly getting to understand that even though whether the piston is traveling, even though the position of the piston is same, that is V1 and V2, or the displacement of the piston is also same, every other condition is same, but only the difference is during the expansion process at one time it is happening while keeping the pressure constant. On the other condition, it is happening when pressure varies inversely with volume. So, these are the two different conditions. It is the same piston, cylinder arrangement, the device is not going to change. The only thing is, in one condition, condition number 1, the piston is moved from initial to final by maintaining the pressure constant. That is one condition. At that particular condition, I am supposed to extract work. In the next condition, I am supposed to allow the gases to expand from initial to final volume, making sure that pressure and volume varies inversely. So, these are the two different conditions. Even though the initial and final points are same, the work done will be different. That is why we call it as the work as a path function. Okay. The point functions are same, but the path function is always different from each other. So, I will take the first condition. When to calculate work, when pressure constant. So, this is the first condition. So, the formula for work, let it as 1 to 2. So, it is product of P into V2 minus V1. So, the pressure is constant here. So, we have written the pressure as P1 is equal to 210 kilopascal. So, V2 is 0.015 minus 0.04. So, by making use of the calculator, we will arrive at the solution of It is 23.1 kilojoules. While solving these kind of problems, we should be very much having the awareness of unit consistency. Here the volume V2 and V1 is in meter cube, both are in meter cube, and pressure is in kilopascal. So only the unit of work what we are getting is in terms of kilojoules. So this is very important. And then let me write the PV diagram for this process. It looks like this. And also for this particular process, I can also understand by the graphical method. So let me say this is the mark of 210 kilopascal, and let this be V1, which was 0.04, and this is V2, which is given as 0.015. Okay. Now the expansion is happening. According to the author, the expansion should be happening keeping the pressure constant. So the initial pressure anyhow is 210, and the pressure remains same. For this particular condition, I can also say that P1 is equivalent to P2. Why? Because the pressure is not going to change. So the initial and final pressure remains same. That means it looks like an horizontal line. Yes, it is an horizontal line, but the volume is going to change. Now this mark is under 0.04, and slowly when it undergoes expansion and reaches the volume 0.015, the PV curve looks like a straight line, and it is a straight line if the pressure is constant. And according to the definition of work, we have already understood in the previous class that the area under the curve in the PV diagram, the area under the curve for this particular figure, this is the curve 1 to 2, the area under the curve is represented, and the area under the curve is always marked with a hatch line so that we can calculate the area. Now the area under the curve, now the entire area is looking like a rectangle. Why? Because the curve is an exact horizontal line, and it always looks horizontal line when the pressure is constant. When the process is constant pressure process, the line on the PV diagram looks perfect horizontal. In the similar way, for a constant volume process, the line exactly looks vertical. Now also by calculating the area of the rectangle also, it has nothing but the formula written for the area of the rectangle, where P is the height and V2 minus V1 can be said as the width of the rectangle. So basically the formulation of work whatever we will be writing in thermodynamics on the basis of W is equal to integral PdV, it will be always representing the area in mathematical terms. So doing that, we have got a value of 23.1 kilojoules. Suppose if you do it in the graph sheet, once again you will get the same value. So going to the next step. So I have completed the first one. So let us go for the second one. So try to accommodate here itself. To calculate work, when pressure varies inversely with volume. So this is how it looks mathematically, that is, I have written pressure is inversely proportional to volume. Suppose if I remove this, if I want to remove this proportionality constant and replace it by a equal sign, then I need to introduce a constant value. So then it looks like P is equal to C by V. It is as good as writing like the circumference S is directly proportional to diameter. The proportional C is circumference of a circle is directly proportional to diameter. If I want to remove the proportionality symbol, then C is equal to pi d. Here pi is nothing but constant. In the same way, whenever in any nature's concept, if we want to remove the proportionality symbol and replace it with equals, they should get a constant introduced. So here the general representation of constant, we have taken it as C as usual. So now if I rearrange this, it looks like PV is equal to C. So in the previous class, we have already understood that if pressure into volume at any given state point remains constant, that means it is a isothermal process. So PV is equal to C is nothing but isothermal process. So instead of author saying this directly as an isothermal process, he has given in a little bit tricky manner, so that once we apply our common sense, so we will get to know the process what has been given as pressure is inversely proportional to volume is nothing but isothermal process itself. Next, once I know that it is an isothermal process, the relation for finding work in an isothermal process is P1 V1 ln of V2 by V1. I can also take it as, I can replace P1 V1 by P2 V2. It's of no problem. Why? Because once I write PV is equal to constant, it means to say that P1 V1 is also equivalent to P2 V2, which is nothing but, generally we represent it as just PV is equal to constant. That means to say the product of pressure and volume at state 1 is equivalent to the product of pressure and volume at state 2. And how does it look like in the graph? So it looks, so this is P1 V1, this is P2 V2, and always one thing we should be keeping it in mind is during the expansion process always the volume is in incremental direction. That means whenever the PV curve is possessing a arrowhead towards right, then you can easily think that it is a positive work produced or it is a positive work done. So in the similar fashion, if the arrowhead is pointing towards left, then it is work done on the system. If it is towards right, it is work done by the system. According to the sign convention which we have already discussed in the previous class, if the work is done by the system, it is to be considered as positive. If the work is done on the system, then the work is considered to be negative. So here, since the gases are undergoing expansion, in both the cases it is positive work done itself. So The final value what we get here is W122 is equal to 11.102 kilojoule. And this is the isothermal process line, or I can also represent this as PV is equal to C. Okay, moving on to the next problem. Let us understand by reading the problem once. A gaseous system undergoes three quasi-static processes. In the previous problem, we have already discussed that the system means it is the working fluid itself. So here it is, the working fluid is gaseous, that is the system is a gas, okay, and it is undergoing three quasi-static processes in sequence. That means there are three processes which are happening one after the other, and there are three quasi-static processes. Okay, full stop. The gas initially is at 5 bar. We have written it in the data also. As the pressure at the initial condition is 5 bar, I have written P suffix 1, where 1 is representing the initial condition and the value is 5 bar. And the volume, corresponding volume is, the initial volume is 0.01 meter cube. Is expanded at constant pressure. So the very first process of three quasi-static process is the constant pressure process. I can write it as, the first one is constant pressure process for my sake of understanding. Okay. It is further expanded according to the relation PV to the power of 1.4 is equal to constant. It is as similar as we have already seen it in the previous class, that is PV to the power of gamma is equal to C, that is gamma is specific heat ratio, and instead of gamma the value has been given it as 1.4. So I can say it as an adiabatic process. The next process is adiabatic process, okay, and it is further expanded according to the relation PV to the power of 1.4 is equal to C to 2 bar. Obviously, once the expansion takes place, the pressure reduces. So the first process's last point is P2, the second process will end up at a pressure of 2 bar. The first process is anyhow constant pressure, that is the pressure will be same at the initial point and final point, and the second process final point will be, that is 2 bar. So this is speaking about the second process. The last one is the gas is then returned to initial state, during which the process PV is equal to C. So we already know that PV is equal to C means isothermal process. So I can write it as the last process to be as isothermal process. Now from the basics from the previous classes, we know that how to identify the lines in the PV diagram. The horizontal line always represents constant pressure process. The vertical line always represents constant volume process. After the horizontal line, the next line what we are going to get is constant temperature line, that is isothermal process line, which can also be represented as PV is equal to C. The next steeper line is after the constant temperature line is the adiabatic line, that is PV to the power of gamma is equal to C. Next there will be another steeper line where PV to the power of N is equal to C. So why I have written these reference lines are, we need to cross check once we start writing the PV diagram. So for the very first process line, hence already we have written the data. So the very first process among the three quasi-static process I have got is constant pressure process. So I will mark a point over here and name it as 1, and the pressure we know it is 5 bar, and the volume is very minimal, which is 0.01 meter cube. So after expansion, keeping the pressure constant, it looks like this. So now the volume has increased, but the pressure is still remaining the same. Next, so the next process is adiabatic process line. Suppose if I see this reference curvilinear lines, I know that the adiabatic process line is much more steeper than the constant temperature line. So I will draw the adiabatic process line and mark it as 3. Now we can see the arrowheads pointing towards right. That means both are representing the process. That means both are work done by the system, or both the processes are giving out work. So only it is pointing towards right. The final process is isothermal process. But what has been given in the final, for the final process, the gas is then returned to initial state, during which process is equal to PV is equal to C. That means from this is process 1, that is constant pressure process. Process 1 is happening between state point 1 and state point 2. This is process 1. Process 2 is taking place between state point 2 and state point 3, and process 3, that is the isothermal process, is happening between state point 3 and the initial point 1. But we should be very careful here. For the third process, 3 is the initial point and 1 is the final point. So it looks like that. So now we have completed the process. Also by comparison, we can see that the curvature of the adiabatic process, that is PV to the power of gamma is equal to C, is much more steeper than compared to PV is equal to C. So now all the process has been represented in the sequence as given by the, or as said in the question. Okay, now we are supposed to find the work done during process 1 to 2, the individual work done during process 1 to 2, and also during the process 2 to 3 and 3 to 1, and finally we need to give or calculate the net work output of the entire system. Okay, so while taking the very first process, which is constant pressure process, so that is happening between the state point 1 and 2. So we know that the work done process during 1 and 2 is equal to pressure into change in volume, that is final volume minus initial volume into pressure. So we know the initial pressure, which is 5 bar. We should be knowing that if I substitute the pressure directly in terms of bar, the unit of work I will be having nothing to write for the unit of work. So first I need to convert bar, which has been given for pressure, in terms of kilopascal or pascal. In this case, we all know that 1 bar is equal to 10 to the power of 5 Pascal. So here 5 bar I am getting it converted to Pascal, so only I have multiplied it by 10 to the power of 5. So the unknown thing here is, we know the initial volume, we know the pressure, but we don't know the final volume. So by the relation of, okay, here the volume V2 is unknown thing, but here the rule is, if I want to find any of the point functions, that is Here at point 1 I have the values P1 V1, at point 2 I have P2 V2, point 3 I have P3 V3. So according to the understanding from process, in process 2 I know, if I know, let me separate this process 2, let me say this as 2 and 3. So generally speaking here P2 V2 and T2, here if I am having P3 V3 and T3, and let me say if any one property is not known and if all the other properties are known, then I can find this property. So in the similar way, so in this case the temperatures has not been given. So P2 is known, P3 is known in this problem, and also V3 is known. So in the process 2, which is happening between the state point 2 and 3, what all we know is P2 is known, P3 is known, and also V3 is known. The only unknown is V2. So to find V2, by making use of the process 2, which is happening between 2 and 3, I am using the process 2 relation and then finding the value of V2, so that I can implement the value of V2 to find the work which is happening between 1 and 2. The thing is, to find V2 I am making use of state point 3. Here there is no facility to find V2, so only I am taking the help of state point 3 to find the value of V2. So by taking the relation between 2 and 3, I am finding V2 and then substituting during the process 1, which is happening between 1 and 2, that is finally we are getting 1450 joules. The next is process 2 to 3, which is a adiabatic process, which is represented by PV to the power of gamma is equal to C. We already know the work transfer equation for an adiabatic relation. So W is equal to P2 V2 minus P3 V3. So in general formula it will be written as P1 V1 minus P2 V2. In general formula it is written with respect of initial and final. Here also we are adapting the same thing. The thing is, in this process between 2 and 3, 2 is the initial point and 3 is the final point. So whatever initial point data is there, we have substituted here as P2 V2. The final point data is 0.3, so it has been written as P3 V3 divided by n minus 1. N is representing the generalized factor. So after solving this, we are getting the work output to be as 3625 joules. So we should make sure, if this work is to be in joule, that means all the units of pressure and volume should be in basic SI units. As pressure here is in terms of Pascal and volume is in terms of meter cube, only then we are getting the work unit to be in joules. If the pressure is in terms of kilopascal, the work comes out to be in terms of kilojoules. The next thing is, after completion of the two process, so we have found the work done during process 1 and also during process 2. Now we are finding the work done during the process 3, which is happening between the state point 3 and 1. So it has been given that PV is equal to C. It is a isothermal process. For the isothermal process, definition of work transfer is P3V3 ln of final volume by initial volume. Here the volume should be a final volume by initial volume. Instead of P3V3, I can also write down the value of P1V1. It is just the same logic. Once we say PV is equal to C, that means to say the P at P1V1 is equivalent to the product of pressure at 3 and volume at 3 is constant. So here it is up to our choice whether to write P3V3 or to write P1V1. Whichever is comfortable, we can write it over there. But while writing ln of, here in the numerator, it should come out to be as the final volume by initial volume. And by solving this, we are getting negative sign since the numerator is smaller than the denominator. For the ln function, whenever the value goes lesser than 1, it turns out to be negative. That is one thing. And also, as we have said earlier, if the arrow mark is pointing towards the left hand side, that means to, or it is representing the work done on the system. Here I can say the process which is happening is isothermal compression. What does compression means? It is the reduction of volume by increment of pressure, and both are taking place. Here we can see the reduction in volume. The V3 is far more greater than V1, or the volume is reducing from V3 to V1. And also we can see the increment of pressure, whereas P3 was less, and as the process continued to P1, the pressure has increased. So we can call it as isothermal compression process. Whenever compression is happening, it is always work done on the system, so only we are getting a negative sign. To get the net work, so summating all of these things, we will get the net amount of work, which is 494 joules.